Welcome everyone to our webinar today. We are introducing a new U.S. CLIVAR working group called Arctic Change and Possible Influence on Mid-latitude Climate and Weather. The co-chairs of the working group are Judah Cohen from AER and Jiangdong Zhang from the University of Alaska at Fairbanks. Both Judah and Jiangdong are on the webinar today. Judah will be presenting. Jiangdong is in Beijing, so he's going to be listening, but if necessary, he can chime in. This is our third webinar and kind of a series leading up to the summit. And we will have our next webinar coming next week. And apologies, I did not have that pulled up. And we hope many of you will be able to join us for it. It'll be on Tuesday, June 30th at noon, and it'll be a presentation from the Ocean Carbon Uptake Working Group. Okay, with that, I'm going to hand over to Judah, who will be presenting today on the new working group. Judah?
Great, thank you, Kristen. I want to welcome everybody to this webinar where I'm going to introduce the new U.S. CLIVAR working group, Arctic Change and Possible Influence on Mid-latitude Climate and Weather. So I hope everybody can hear me clearly. And I also just wanted to say to those that are members of the working group, you know, I'm representing not just myself, but everybody in the group. And if I neglect to say something or I say something wrong, please chime in, whether it's through that raise your hand button. But you can just certainly feel free to jump in and let me know and help and correct me. Okay, so with that started, I'll just move on to the next slide. So I think certainly this is a very timely working group. Here's just some examples of weather or climate events in the news. Certainly, I start with my own personal favorite. One that I got to live through myself was the very winter with extreme snowfall and extreme cold this past winter. But more recently, we've had the flooding rains in the southern plains in Texas and Oklahoma. Been a big problem for that region, and not just U.S.-centric, but there was a recent heat wave in India, supposedly it's fifth deadliest on record. That should be mostly over now with the coming monsoon. And then, of course, there's the ongoing drought in California, which will definitely not end anytime soon. So here, the outline for the talk. So first we're going to talk about Arctic amplification. The past 2 decades, the Arctic has been warming more than twice as fast as the rest of the globe, and this is what we refer to as Arctic amplification. Concurrent with Arctic amplification, extreme weather has been observed to be increasing. So certainly, certainly the public, and I think the press have been quick to link the two. And there have been also numerous theories linking Arctic amplification to more frequent extreme weather and climate events. Though testing these theories is challenging due to large natural variability, short observational record, and model shortcoming and conflicting results, and that's something that I'll touch upon in the talk. But the good news, I think we've really assembled a great group of scientists, really leaders in their fields to study this, that are studying this topic, and I think I'm confident that we'll be able to move the science forward, through our meetings. Hopefully, we're going to be productive in coordinating studies and come out with some future publications. Okay, so I think the poster child, and hopefully the whole slide is visible to everybody. But the poster child for Arctic change anyway has been the melting sea ice, and here's kind of comparison from 2007 back to 1979. So certainly not that minimum sea ice minimum has been eclipsed in 2012, but I think it still shows very telling, the decrease in the sea ice compared to maybe the climatology and certainly the earlier part of the satellite record. And especially striking is the change in the multi-year ice, and really kind of in this new regime where the Arctic basin is really dominated by first-year ice. But it's not been just sea ice that's been melting rapidly or disappearing rapidly. Snow cover across the whole northern hemisphere in the warm seasons, summer to a little bit, but really especially in spring, has been melting supposedly even quicker than the sea ice. So I plotted up here, September sea ice and June snow cover, and seems like the decline is pretty comparable between the two. I thought it was I didn't realize it was quite striking. I put up the correlation between these two time series, the September sea ice and the June snow cover. There's no reason why they should necessarily be strongly correlated, but they quite are. They are, and even during this era of the emergence of Arctic amplification, interannual variability is also strikingly quite similar. So maybe something to take up in the future. But anyway. Okay, so if you look at just the top panel first, if you just do a trend analysis of surface temperatures, and this is limited to the winter, you get, I think, the result that everybody is expecting. The field is projected or predicted, with pretty much widespread warming throughout the whole hemisphere, and with that warming accelerating towards the high latitudes, towards the Arctic, and on the left side of that top figure, you can see the zonal trend, trend for each latitude, and so you get a warming trend, certainly for all latitudes, but it's more muted at lower latitudes, and then it really increases rapidly as you get kind of poleward of 60 north. But if you kind of split up, look at the time series of the warming trend, you just do a time series of the temperature anomalies for the Arctic alone, 60 to 90 north, and then the rest of the hemisphere. So outside the Arctic, outside the polar regions. If you look most of the record, actually the time series, the trend is pretty consistent between the two. There really is no amplified warming, let's say, in the Arctic relative to the rest of the hemisphere. It only started more recently, certainly post-1990, I guess the exact date might be somewhat up to debate, but let's call it from 1990. That's where you really see the divergence in the temperature time series, where the Arctic is warming much more rapidly than the rest of the hemisphere. And if you do now take the trend analysis and you limit yourself just to that era of where the polar amplification emerges, the Arctic amplification emerges, you get quite a different hemispheric temperature trend, where you get very strong warming in the Arctic, much more so. So really, this amplified warming that you see over the whole record is really from the most recent period. And then you get in the mid-latitudes, you actually get cooling, and I think this is a very interesting and surprising result. And if you look at that latitudinal temperature trend, you get some warming in the subtropics, and then you actually get cooling over the mid-latitudes, and then a very strong accelerated warming as you get to the higher latitudes. Now, I showed winter. If you kind of look at the trends broken up by season, you see that this is really a phenomenon that's limited to the winter time. So the top plot is for winter, and then you have spring, summer, and fall on the right-hand side. And you can see for spring, summer, and fall, the warming is pretty widespread through the hemisphere. There are some regional cooling areas, but the warming is quite widespread, especially in the summer and the fall. And all those three seasons, spring, summer, fall, have this pretty consistent warming trend. I mean, the one exception is the winter, and especially in the most recent period, you can see is actually the cooling seems to have been even to be accelerating. So if it certainly seems from this, just looking at the different seasons separately, if possibly, something that's a surprise, something that's different from what we expected, it's in the winter time, and maybe if there's a role for this Arctic amplification, Arctic change to be forcing weather mid-latitude. So I think winter quite jumps out, but the idea of Arctic amplification influencing mid-latitude weather is certainly not limited or isolated to the winter. It's also been for all the seasons, especially I think outside the winter, especially summer, and I'll talk about that later, in the webinar. So okay, I talked about the Arctic amplification. Now what about extreme weather? So I mean, climate change on itself predicts that there'll be an increase in extreme weather, and particularly in hot weather, high temperature extremes, heat extremes, and in precipitation events, both increase in the heavy precipitation events and also in a possible increase in drought. So a lot of the variables that are plotted up here that we plot in our paper have to do with the hot extremes and precipitation, heavy precipitation events. And if you look at the latitude and longitudinal distribution, the horizontal distributions, they've been increasing pretty uniformly, or not maybe not uniformly, but increasing throughout the mid-latitudes. Those are the heat extremes and the heavy precipitation events. And if you look at certain time series like these warm summer months or very wet precipitation, you can see that they've been increasing over the record, especially over the most recent records since this emergence of the Arctic amplification. Also plotted here some cold extremes, cold months and temperatures below freezing, days that have temperatures below freezing, and certainly consistent with what we've expected. There's been a decrease in those cold extremes, though there's kind of this flexion point also kind of during this period of Arctic amplification, so that those decreases in the cold extremes has kind of stopped and reversed, and we'll see if that's temporary or not. So that, again, something not really expected and is interesting. And so is Arctic amplification, is it possibly playing a role in both these heat extremes, heavy precipitation events, maybe even this reversal in the cold extremes? So maybe kind of looking at some individual type extremes. So here's a plot, of snowfall and extreme snowfall events in big northeastern U.S. cities, and I think it's quite striking. Here's going back to 1880, and separated out, pre-1990, post-1990, kind of again this era of the emergence of Arctic amplification, and I think you would agree that the frequency has really increased quite a bit, and it's almost as if there have been as many extreme snowfalls in the past 20 odd years as there's been over the whole record, extending back over 100 years. So it certainly seems like there's been this, at least temporarily, we'll see if it continues, but at least temporarily this spike in the frequency of these extreme snowfalls. And again, this event that certainly was quite impressive, that the rainfall in these southern plains, a figure I got from Simon Wang. If you look at the stream function, the trend since 1981, and then this past May, the anomalies, you've had this trend of this, at least in the month of May, kind of this ridge trough pattern that advects moist southerly flow into the southern plains, and that certainly was very much amplified this past spring, and was certainly helped to produce the record wet. Well, actually, it was a record wet month for the entire United States, but especially focused on the southern plains and resulted in those devastating floods. And here's a plot that just I actually got from Jennifer Francis, but I guess the source is Munich Re, so from the insurance industry, but just trends in extreme events. They're both weather and climate events and geophysical events. I mean, the geophysical events are kind of this red maroon color, and there's no detectable trend in that. But in the weather and climate events, there's been clearly, at least plotted up here, and I'm not sure if this is based on infrastructure, societal metric or weather metric, but meteorological metric, but certainly there's been this very clear increasing trend in all types of extremes. And there's a diagnostic, so kind of trying to make that connection now. Talked about the Arctic amplification separately, talking about extremes separately. Maybe how to connect the two. And diagnostic that I like to look at is this polar cap and geopotential height. So it's just taking the area average and geopotential height anomalies over the polar cap poleward of 60 north. And I've plotted out the daily trend from October 1st through March 31st. And height, the geopotential height, especially in the freestanding atmosphere, is a very good proxy for temperature. And you can see that throughout the entire cold season, the fall and the winter, there's been this increasing in geopotential heights, and with that, there's been this increase, in temperatures. And it's not just limited to the lower boundary layer. It's throughout the atmosphere and the atmospheric column, and it even extends all the way, into the troposphere. Into the stratosphere, especially, in midwinter. And this is, this plot by itself kind of is suggesting, obviously, about the warmer Arctic, but also that you have increased polar troposphere stratosphere coupling and a more negative AO, or weaker polar vortex, in the fall and winter. And here's just for one individual year. Here's that polar cap height. So these are anomalies, not a trend, but for 2012-13. And you can see that it's dominated by red throughout that October 1st through March 31st time frame. And you can also note the stratospheric warming there midwinter in January. So consistent with the trends. And then if you plot it now, I've shown on the top plot is if you regress the anomalies of sea ice, well, how did sea ice contribute to those polar cap heights? So you can see that the sea ice is only contributed, to much of that polar cap height, those positive polar cap heights, those high heights or those warm temperatures. The sea ice contributed quite a bit to it. And then I also have these yellow bars, and it kind of lines up with these extreme events that happened throughout those 6 months. I think it's 6 months. From October through March. So there was these severe winter weather, not just winter, but it started with Sandy. So there are quite a few extreme events scattered throughout the whole northern hemisphere, and they really match up very nicely with, first, the contributions that you see from the sea ice, but also where I like to refer to as these pulsing of the polar cap ice, where the Arctic, warm, the amplitude and the warming, and the amplitude of the higher heights is amplified. And when you get these pulsing of the polar cap heights, then you really seem to have much higher likelihood of an extreme event, in the mid-latitudes.
Judah, Greg has his hand up. Can I see if he has something to contribute to that?
Who has his hand up?
Greg.
Okay, sure. So should I pause here, or?
Yeah, Greg, you're off mute. Did you have something to add to Judah's presentation or a question?
I just wanted to ask a question. That is the correlation with sea ice. What is the mechanism, do you think, by which sea ice is correlated with these anomalies that seem to be predominantly in the free atmosphere? And I would have thought that sea ice connections would have been, had their biggest signature near the surface.
Yeah, so this is a question that the community, I think, is trying to grapple with. Certainly the anticipation was it should be near surface, and I think certainly some modeling results have shown that near surface, but other modeling results have shown that those warm anomalies from the melting sea ice can penetrate throughout the atmospheric column, and I think we're trying to understand those mechanisms. I'll talk briefly how that can happen, later on in the talk. But I think remains an open-ended question.
Great, thanks. Continue, Judah.
Okay. So extreme weather, so just kind of bringing some points about that. There's problems when we're trying to talk about extreme weather. On its own, even besides trying to relate it to Arctic amplification. Extreme weather is subjective and not well defined. It's predicted to increase under climate change. You don't need to invoke Arctic amplification to explain an increase in extreme weather. So it'll certainly be a challenge for the group to identify which extremes may or may not be influenced by Arctic amplification. And I just want to make the point clear that we're not just going to focus on extreme weather, but rather, first order, we're going to look at the linkages between Arctic amplification changes in the atmospheric circulation. But certainly, I think what the public is most concerned about and what they're most interested in is in extreme weather. And so I think we have to be sensitive to that and try to make advancements on that end. Okay, so there I've kind of try to summarize these theories linking Arctic amplification to mid-latitude weather. So I think the one that most everybody would agree upon, is in play is that with the Arctic amplification, you change the latitudinal temperature gradient. That seems very, very intuitive. If obviously the Arctic is warming faster than the rest of the globe, and the Arctic is colder than the rest of the hemisphere anyway, then you've relaxed, you've weakened the equator to pole temperature gradient, this latitudinal temperature gradient. And certainly, through just the simple relation of the thermal wind equation, that weakening of the latitude temperature gradient should lead to a slowdown in the zonal wind in the jet stream. That again, I think, at least if you certainly weaken that near surface temperature gradient, that I think everybody would agree that certainly should be an outcome. What's less agreed upon, though maybe somewhat more controversial, or apologize for that, is then these add-on effects, these follow-on effects, where changes in the slowing of the jet stream could then lead to increased blocking, higher amplitude waves, and slower wave speed for these waves, and that certainly can lead to more persistent extreme weather. Besides changes to the jet stream, there's also changes to atmospheric waves. So, and kind of this seems a bit of a split here between winter and summer, where the winter, the changes to the waves are in the larger waves, the planetary waves, wave numbers 1 to 3. And in summer, it's to smaller waves, these synoptic scale waves, let's say wave number 6 to 8. Also, besides changes to waves, there can be also changes to troposphere-stratosphere coupling. And again, I think an important caveat here is that there are these, quite a few theories, and there's certainly been quite a few papers and more coming. But support for these theories are conditional and challenged by the imperfect observations and by the models, imperfect models. And certainly this is I think, is a work we need to deal with very, very closely. So again, trying to talk about these different ideas. I think one idea, maybe the one idea that has been written the most, you've seen the most articles in the literature, is this decrease in sea ice in the Barents-Kara seas, especially in the winter time. That low sea ice seems to promote, again, going back to that polar cap heights, we had the low sea ice leads to the increase in the geopotential heights, leads to stronger high pressure, and in that region it's the Siberian high, so it's kind of this northwestward expansion. I like to think about it as a northwestward expansion of the Siberian high. So we have high pressure, spread out across the Asian northern slope. That leads to more vigorous northerly advection. That's cold air advection into Central and Eastern Asia. And there's a couple of papers put down, but there's certainly a lot of other papers that have come out on this idea. But this is not just limited to the Asian continent. There's something maybe analogous, to the North American. We're showing here a positive P&A pattern, something that's been, they call it ridiculously resilient ridge. So there's been this, for the past 2 years, and it's really dominated the weather here in North America, this strong ridging in the Eastern Pacific, Western North America, and then this downstream trough in the Eastern U.S., and it's led to these, 2 record cold-breaking winters here, but it's even persisted in the summertime. And actually, I write this kind of this AO blog, Arctic Oscillation blog, and it talks about upcoming weather. So here's actually a plot just generated today. I have it on the right, and so if you're not following the weather, there's a good heads up. We are going to get this very similar type pattern. All the players are in play here with this strong ridging in the west. So record heat in the northwestern U.S. is coming up, and if you like your end of June or early July hot in the eastern U.S., that's not going to happen. Got a very impressive looking trough for this time of year. It's almost a winter type pattern superimposed on the summer circulation. So anyway, I thought certainly everything we're talking about is very is current, and it's even you can see it in play even in the next few weeks. Besides sea ice, the impacts of maybe sea ice on the circulation, I certainly don't want to neglect my own ideas. With myself, my colleagues have put that Well, Arctic amplification leads to a moistening atmosphere, and that could certainly possibly lead to an increase in snow cover, and that has been what's been observed. Some people would disagree, but I think at least from the satellite data, it's showing this increasing snow cover across Eurasia, and not just Eurasia, but in particular across Eurasia in the fall, and October is the key month. And then when you have high snow cover, that has, we've argued that leads to more vigorous stratosphere-troposphere coupling. You get a weakening of the, you get more energy transfer from the troposphere to the stratosphere, weakening of the polar vortex that propagates down to the surface. You get this negative Arctic oscillation and an increase in Arctic outbreaks and snowstorms. And since then, a similar idea has also been, I think, adopted by the sea ice community, where they've tried to also argue that less sea ice, so you have more snow cover, but less sea ice also leads to this more vigorous troposphere-stratosphere coupling. Here is an example from a paper in Kim et al. It came out last year, about a year ago, also showing this more vigorous troposphere-stratosphere coupling, a weakening polar vortex, and negative AO. But these ideas with sea ice and linkages to mid-latitude weather is not limited to the winter. Here's a recent paper showing changes to summertime. So we have, again, this idea that I discussed about weaker temperature gradient, latitude temperature gradient, a weaker zone of wind. This paper by Camus et al. Showed that weakening in the zone of wind has a strong relationship to temperatures. We have more high temperature extremes when you have a weaker zonal jet, and that relationship is particularly strong across Europe, and shown here is that relationship with Moscow. Certainly it would make sense for Europe. Seems to pretty logical, a weaker wind. So Europe is cooled by the penetration of maritime air into the continent. You weaken the winds, you have less a breakdown of that penetration, and then a buildup of heat over the continent. Though I guess I think this summer is not working quite out. That seems like it's been pretty cool in Europe, and doesn't look like that's going to change anytime soon. So again, maybe this kind of an overview from a recent review paper from Overland et al. What's this linkage between Arctic amplification and mid-latitude weather? It starts with you have this Arctic amplification, the temperature increase over the pole, preferentially. That leads to higher geopotential heights over the pole region, warmer temperatures. Then you have a slack of the westerly winds. I think that pretty much everybody would agree with. But then it gets a little more less understood, let's say. Then there's ideas that, well, if you have a weakening zonal jet, that leads to a wavier jet stream, increased blocking. Now weather patterns move eastward more slowly, they're more amplified, they're more persistent, and you have an increased likelihood in extreme weather. Again, this idea, certainly first put forth by Francis and Vavros, that with the warming of the higher latitudes preferentially, that leads, so you have the ridges, these ridge troughs patterns, these waves in the atmosphere. The ridging, increases towards the pole quicker than the troughs do towards the pole. So you kind of have a stretching, increase in the amplitude, of these waves, and that leads to more amplified and persistent wave patterns. Again, this same positive P&A pattern that people have been talking about, and certainly the nature has, delivered. It's been very persistent. But the problem is that, certainly one challenge, touched upon, but I'll spend a little more time talking about, the role of natural variability. The natural variability in mid-latitude is quite large, and it's really a challenge to separate the signal from the noise. There are many factors influencing mid-latitude weather, and isolating just one factor is difficult. We know that the tropics and the mid-latitudes influence the Arctic, and therefore, really, the Arctic amplification that we see is more of a response rather than a forcing factor on its own or a cause. So this really complicates, our studying between Arctic amplification, mid-latitude circulation, and extreme events. But also extreme events are infrequent, are poorly absorbed, and the definitions are subjective, and may be more societally based than really from a meteorologically based. And so we're going to have to try to separate that out. Again, just trying to, this figure's just trying to summarize those challenges that so the double box is the is the pathway that's been kind of argued by by some that this Arctic amplification is influencing mid-latitude weather, but there are many factors influencing mid-latitude weather, and separating out just one factor, let's say Arctic amplification, is very difficult, and it certainly may just be within the in the noise, and there's signals will never be pulled out. And here's an example of just showing the large variability. This is from Elizabeth Barnes, and if you just look at, so we talked about changes in the jet, but if you look at the winter jet in the Atlantic and look over the whole time series, let's say over the reanalysis time series, and you look at the most recent period, it doesn't look any different. The behavior is consistent with what we've seen over the historical record. It hasn't really hasn't emerged beyond it. There's nothing outstanding about it. Certainly it's not greater than what the very large variability that's just inherent in the system. And besides just natural variability, so there are also these modes of natural variability that are that are happening, that are forcing the system, the mid-latitude weather. So one of those modes is this AMO or AMV, Atlantic Multiplicator Variability, and this is from Yannick Payne's, his work with Gudrun, that the AMO can force this pattern that looks very much like the Arctic oscillation that's been related to changes in Arctic amplification. So this idea of increasing geopotential height to warmer Arctic can be forced by just other modes of variability that are outside the Arctic. And here, this is one that's related to the North Atlantic Ocean. The circulation in the North Atlantic, well, I guess it's the whole Atlantic, but certainly focus on the North Atlantic part. And besides, say these modes of natural variability, such as from the oceans, there's also forcing from the tropics. So here's just a modeling result. Again, looking at this ridge trough pattern that we've been so persistent. This is from, I guess, the winter of 2013-14, but that ridge trough pattern has been so persistent. This modeling result just quickly shows that pattern can be forced with tropical forcing alone. You don't need. I mean, there's certainly a contribution in their model results from the Arctic, but you're getting the same type of forcing from the tropics. And again, this idea of let's say you get this negative AO and this weakening of the poleward flank of the jet, weakening of the polar night jet, in the stratosphere. Here's just a modeling. I think this is a modeling result. I think. I guess John Duncan. But anyway, this is just based on tropical forcing. So this idea of this equatorward shift, let's say in the jet, you're getting that, which has been associated with Arctic amplification. You're getting that same exact atmospheric response just from tropical forcing. Okay, so going forward, and with the research has been done so far, and the research going forward, there are challenges that are not going to be easily overcome. One is that there's the short time series of observations. We've talked about the emergence of Arctic amplification is only since 1990. That's 20 some odd years, not a very long record. There are model deficiencies. I mean, we know there are shortcomings in the model with boundary forcing, especially in the high latitudes between snow and the ice. Modeling studies up till now have really been pretty much uncoordinated, and it's been almost like comparing apples to oranges. And also there are large biases and uncertainties in these matrices that we're using for analysis. Kind of just trying to reinforce that idea of the observational record. The length of data is 10 to 20 years. It's short and it's chaotic. The variability, not the natural variability, is quite large, and it makes even with a short record, even with a longer record, it's difficult to pull the signal from the noise. And there are many, again, reinforcing these. There are many factors that are forcing mid-latitude weather, and to pull out just one factor is quite difficult. And the observational network in the Arctic is sparse. And also, again, these very conflicting results with models. Again, here's a slide from Elizabeth Barnes on modeling studies, but the point is that here are two models that were forced with the exact same sea ice, and they got very different responses, where one model shows a poleward jet shift, and the other one shows no jet shift. And so how what's really happening? What is the one that's the best representative of the natural system? So, but challenges are great, but I think the good news, we've got really a great team to tackle these challenges. And I won't go through everybody's name, but I think everybody on the phone would agree that this is a really great, really the top experts, in this field. And I feel very lucky, and I feel really lucky and fortunate to have all these scientists agree to participate in this working group. And we've got quite a varied expertise, modeling, and observations. There have been some previous workshops. I'll list, I haven't listed all of them, but I think this kind of summarizes the different outcomes, conclusions from those workshops, and it'll just kind of, these kind of sound familiar from the previous part of the talk. There's large gaps, from this National Academy of Sciences workshop in September 2013, large gaps in our understanding. The observational record is short and the modeling studies are conflicting. There was a workshop in Reykjavik, Iceland that soon followed. The topic is controversial. There's little agreement on the mechanism, but it's a major science challenge, and certainly there could be some really great benefits, like improvements in long-range forecasting. And then there's a more recent workshop here in Barcelona, Spain. Again, attribution is controversial. Then there's, I guess, maybe this newer idea that linkages may be regional. You don't have to think about it as hemispheric. But again, there's this very strong potential for improving seasonal forecasts. Again, this is a slide that James Overland contributed, and kind of maybe this new consensus is starting to emerge. Let's see, maybe there's some agreement on these ideas. Most studies on Arctic amplification mid-latitude linkages favor early winter linkages. This has to do with that Barents-Carrot sea ice that I showed very early, that are regional and based on amplification of existing weather patterns. So that like that northwestward expansion of Siberian highs, I mean, that happens, naturally anyway, even without amplification. Maybe amplification is just reinforcing, amplifying that variability. The linkage are a combination of internal variability, two-way, so it's not just the Arctic forcing the mid-latitudes, but we have to recognize and be sensitive to the fact that mid-latitudes are forcing the Arctic and also the tropics. And all these things are important, in the final result that we observe in the mid-latitudes. Maybe a possible way forward is investigate multiple dynamic processes that are kind of buried there in the noise. We need a grand science challenge to increase our understanding. And it's certainly worth further investigation because there could be some very nice potential payoffs, including improved seasonal forecasting, especially if the Arctic continues. Well, I mean, this idea, but if this idea holds true that the Arctic is really has an influence on the mid-latitudes. So the proposed task, for the working group, we wanted to see, as much as possible, extend the observational time series, recommend new observation. I think this would be, really great if we can do this as a group, have standardized modeling studies. So try to get to a better understanding what the models are showing us. To that end, have coordinated modeling studies with large ensembles and case studies for identifying physical processes. We're not trying to work in a vacuum here, but work with the community-wide. So we're going to make great effort to coordinate with other Arctic groups, SURGE, CLIG, IASC. At the end of it, we're certainly trying to have some kind of synthesis review project. So one idea was a review article, but what's being more favored by the group is kind of a journal special issue because it's still very controversial. The spectrum of ideas is quite large, and maybe multiple articles on, related to the same topic might be the way to go. So for meetings, we're going to have bi-monthly, even maybe early on, monthly teleconferences. We have our annual meeting. I think it looks like this is pretty much a done deal. Will be held at fall AGU. And then a year from following that, we'll probably have a workshop, but this working group is just getting off the ground, so a little premature to talk about where that might be. And what are the expected contributions? So certainly better understanding of the knowledge gaps, a better use of the observations, standardized modeling studies, a better understanding of what is the model response, what's the simulated model response to Arctic amplification, and hopefully one payoff anyway is improve climate prediction. So here's my last slide. So just summarizing, the past 2 decades, Arctic has undergone rapid and dramatic changes. I think we all recognize that. Strong warming and large variability in sea ice and snow cover could be influencing mid-latitude weather. But again, there's a lot of challenges making that argument more convincing. Many theories, studies argue or show that the Arctic variability influences mid-latitude weather through wave interference and/or jet stream characteristics. Skepticism remains high due to large natural variability, short observational record, and inclusive ambiguous modeling studies. So, I think that, I think I should have, express the idea that, the jury is out. It's not like, one idea is not, is kind of, we're just going to promote just one idea, but we're going to try to, come to the truth, whatever that idea might be. And we'll certainly give all ideas equal attention. But I think, the challenges are great, but I think we've also have a great group of scientists that we've gotten together for this working group, and I think certainly couldn't be more timely for this working group to get together and to make some progress. So thank you. That's the end of the talk, and I just was going to maybe I don't know. I had a animation, see if it comes up or not. Just kind of showing this weakening of the polar vortex. This is from, again, that 2012-13. But I mean, it just shows you, that when you break, when you have this warming of the Arctic, you really have. I think it shows very nicely in an animation like this that you really change the mid-latitude weather. You can see, the reds and the blues can be representative of temperature and this, with strong warming in the Arctic. This is in the stratosphere, but still strong warming in the Arctic leads to big changes in the mid-latitudes. And also you can see that warming very much comes out of Siberia. So, an area that we've talked about as a hot spot. So I guess hopefully we have a little bit of time for some questions. I don't know if any hands have come up.
Yeah, thanks, Judah. If you have any questions, feel free to go ahead and either raise your hand or type it in the chat box, and we can either address them from the chat or we will take you off mute. Looks like AK, and I am guessing this is Arun Kumar. And you are off mute.
Yeah, that's me.
Hey, Arun.
Hey, great summary, Judah. I have a question on your slide 5, which gives the correlation between sea ice and the snow.
Right.
Did that correlation include the trend, or did you remove the trend before the correlation?
Yeah, that's with the trend removed.
Oh, okay, that's pretty.
I mean, that's a published result, so 2013 paper, but that's with the trend removed. I don't think it's slide 5. You went past it, I'm pretty sure.
Slide 5?
It's not slide 5.
Slide
no.
5.
It's after slide 5.
Oh, I'm sorry.
It's like,
it is on slide
12
5.
or something. I don't see it.
You see it on the screen now.
Oh, you do?
Okay, thanks.
It's more like 13, 14. It's 14.
Okay.
All right.
Another question? Thanks, Arun.
And again, if anybody who's part of the working group and you're listening to the talk, if you feel like I wasn't clear about a point, or that something could use some further clarification or added, please jump in and be happy.
Judah, Moyan Wang wanted to ask, which part of the snow cover are you talking about?
Well, I mean, there were two. I went through it a little bit quickly, but so there are two. I mean, the very first part of snow cover I talked about was hemispheric spring-summer snow cover. So that's showing the large decreasing trends. But then there's also, in the fall, there's been these strong, certainly statistically significant increasing trends. What I'm referring to is across the Eurasian continent. I mean, at that time of year, October, it's really Siberia. But I'm pretty sure that those increasing trends have been also happening in North America. I don't think as strongly, but I think it's not just limited to the Eurasian continent. But I think it's been more pronounced in the Eurasian side. just last fall, obviously what got in the news was the large warming, but it was record extensive snow cover across the northern hemisphere last fall. So, I think it's pretty, and I don't know if people realize that, but I think it's a pretty surprising occurrence, especially given how warm it was.
Great, and we have a question from Alessandra. Alessandra, you're off mute. Go ahead.
Hi, Kristen. Hi, Judah. Yeah, I have more of a programmatic question. I wonder if you have what your contacts are with international CLIVAR or other groups outside of the U.S. that may be working on related issues, or whether there's grand challenges in CLIVAR that this.
Yeah, I mean certainly. Certainly, we want to coordinate and collaborate with international CLIVAR, so that's certainly one of our goals, and other international groups. I mean, certainly I've listed search. We have some search members. I'm not sure if search is international, but. Well, I guess we had our first webinar. We definitely talked about coordinating with international CLIVAR, and I think Mike Patterson has been actively doing that. And if Mike, you want to chime in, you can jump on board. And also, I guess we're going to try to coordinate with with CLIC and Polar Prediction Project as well.
Thank you.
But we are definitely trying to coordinate with these other international organizations and committees.
Great. Mike, did you have anything to add to that?
Yeah, I just wanted to echo what Judith said in terms of there's a WCRP Grand Challenge on melting ice and global consequences, and this topic fits nicely within that portfolio. Internationally, that effort's being led, I believe, by the CLIC Scientific Steering Group, and we have Greg Plateau online. He's a co-chair of that group. They've also helped sponsor some of the previous workshops internationally on this topic, so we do have a keen interest in seeing that connection to the international effort made through this working group. We also have intentionally included some international members or U.S. members of the international CLIC community within the working group makeup to help foster those links as well. But we anticipate that moving forward we'll be providing regular updates to CLIC and international CLIVAR insofar as they have this newly forming climate dynamics panel that will probably be the primary intersection with this grand challenge on this topic. But that has yet to meet and spin up. That's all.
Great. Thanks, Mike.
Yeah.
Judah, we also have a question from Diane Statinsky from NOAA. She wanted to know, as part of the group's efforts, will there be a push for or focus on new and emerging technologies to help satisfy the need for additional observations in the Arctic?
Yeah, I mean, I don't. Maybe someone else as part of the group it would be better expertise to answer that question. I mean, certainly one of the challenges we like to take on is to suggest, new observation. What new observation in the Arctic would really help in understanding this problem. To understand what is the, what if any is there linkage between the Arctic and the mid-latitudes. So I don't know what new technologies we might be able to recommend. Myself probably couldn't recommend anything, but I think as a group we could certainly recommend maybe what type of observation would really help. What's currently missing. That what if was brought on would really enhance and mitigating these knowledge gaps. So, but certainly we have people that are actively involved with observing the Arctic, in the group, and certainly. I don't know. I mean, again, if one of them jumped on, maybe they could help me out here. I don't, but if there's a possibility of new technologies or some kind of remote sensing, I don't know. But I think we do have people that are that are better equipped to answer that question.
Great. Is there anyone on the call from the working group that wants to further add to that question? Raise your hand and I can take you off.
And I know, one person is Ignatius Rigger. He's not, I think he emailed me. They unfortunately won't be able to make it, but
correct. Yeah.
So others, maybe we can help out.
Good. Thanks, Judah, and thanks, Diane. Any other questions from the group? Okay, I don't see any hands, and doesn't look like anything's being typed in the chat box. Okay, I think we will go ahead and wrap up here. Thank you everyone for attending the webinar today. As I mentioned earlier, I will send around a recorded archive version of this that you can view and share with any of your networks and colleagues who you think would be interested in the new U.S. CLIVAR working group. Thank you everyone and have a good afternoon or morning, depending on where you're calling from. Cheers.
Thank you everybody.